Hello, everyone. Thank you for being here today, joining us in the discussion about radar-centric integrated sensing and communication. In our previous interviews, we had experts from academia, but today we have the pleasure to talk to Dr. Kumar Vijay Mishra in the US Army Research Laboratory. He's also an advisor to several companies working in different areas like automotive radar or imaging radar. He's a very active member of the ISAC community, leading several initiatives like an upcoming book on signal processing for joint radar and communications, where he's being the lead editor. Thank you, Vijay, for accepting my invitation today and for sharing your radar expertise with all of us today.
Thank you, Professor Gonzalez Prelcic. It is a pleasure to be here, and I'm very thankful for this opportunity to discuss some of the recent research questions on this topic.
I would like to start the discussion with a question about how intelligent reflective surfaces can help to enhance performance in joint radar and communication systems. It seems there are many researchers skeptical about the possible benefits due to the attenuation that depends on the fourth power of the distance. So what's your opinion on this idea of using the signal bouncing on a wrist for radar functionalities?
You're very right that there has been an explosion of publications and research activities on this topic on use of intelligent surfaces. And if I may paraphrase this question a little bit, or maybe expand it a little bit, I would say we need to think about intelligent surfaces in both ways, not just as reflectors where they are part of the channel for radar and communications, but also their use as a transmitter, as being close to the transmitter and acting as a part of the transmitter.
It's a different use, yes.
Yes, and in both cases, we have certain advantages that these surfaces could provide. So let me focus on the first aspect, that is the reflecting surfaces where they are part of channels first. So as you rightly mentioned, in communications, researchers are looking into how this can help in extension of coverage of the communication system. So if you put a reflecting surface in the channel, there are areas that where you couldn't reach earlier. This surface could act as an intermediary to carry forward the signal to those regions. Another aspect could be in radar. In radar, typically it's a line of sight operation. And if we want to look around the corners in a vehicular system, or we want to just do in general non-line of sight sensing, then these surfaces, they offer very attractive features in that way. But if they are only reflecting and passive surfaces, in that case, clearly it is an issue because as you mentioned that in radar, the received power is inversely proportional to the fourth power of the range, and it declines very sharply in the case of radar. So the advantage that we are relying on here is that there are two features that we could exploit. First is, with large number of elements, such a surface may provide some gain for a particular range from the radar. So at very far range, where the signal becomes very weak, a reflecting this kind of surface, intelligent surface over there, may provide some gain compared to the line of sight path. That may not be the case in every line of sight range, right? If you're nearby, then the line of sight is already very strong. But when you are in the far range, in that case, there is this sharp degradation of received power, but putting the surface to detect very far off targets may have some advantage. Second feature that we could exploit is, although we talk about reflecting surfaces as completely passive, it is indeed possible to impart some active sensors to that surface, which we call as active beamforming or surfaces with RF chains. So they are not just passive reflectors. In that case, some gain may be imparted to them. And again, the advantage for radar would be in far off ranges where the line of sight is weak, you put these kind of surfaces which may enhance detection in far off range. For nearby range, I think the line of sight signal may be fairly strong for the radar to detect without the aid of intelligent surfaces. And second, for non-line of sight cases around the corners and so on, these kind of surfaces may help the radar system to detect those kind of targets. So this is when it is a part of the channel itself. However, it becomes more attractive when it is a part of the transmitter. So we were just talking about in full duplex, how we can enable simultaneous transmission and reception, multi-beams. And these are the features which intelligent surfaces can impart. Because intelligent surfaces or these kind of reconfigurable meta surfaces also, in some of the literature uses that term. The surface may have non-reciprocity property. It can do multiple beams in different directions. It can also embed polarization within the transmitter, multiple polarizations, and you can use that function as well for this, for separating radar and communications, for example. So when it is a part of transmitter, it makes transmitter very flexible. A lot of interesting features we could experiment with. So I would say, yes, it is a very interesting development.
Let's keep talking about hardware. When designing communication systems at high frequency bands, one potential MIMO architecture is based on using low resolution ADCs or DACs. However, traditionally radar operated with high resolution converters. Do you think that low resolution architectures are feasible when sensing also comes into play and we move to the design of joint sensing and communication systems?
Yeah, thank you for this question. There's another interesting development taking place in our community, use of low-res ADCs or DACs for radar. In recent times, there has been indeed some work on exploiting these features for radar as well. Like we talk about 1-bit radar sometime, where these features have been employed. Many of these architectures, they rely on some of the theoretical results where it has been shown that under certain circumstances, use of these low-res ADCs can help in recovering the full precision data, including in radar. It has been shown under certain circumstances with some bounded error. For example, there is one approach I remember where Bus-Gang theorem has been used to implement this 1-bit radar. However, the shortcoming of that approach, I would say, is that it is only for the Gaussian case. So only when there is Gaussian noise, then they have shown that you could apply such theorems. And there are other approaches also that I've seen people have implemented. In radar, the radar community, especially in military applications, is very concerned about having a very near perfect detection performance. So when we are talking about that, okay, I can recover this full precision data with some bounded error, people usually balk at those kind of results that, okay, but we don't want these kind of statistical errors inbuilt in the system. If we are getting a good performance with full precision data, because especially in military, cost is not a constraint. So many of these architectures, they are helpful in realizing inexpensive systems instead of using these full precision ADCs, etc. We would like to use inexpensive systems. But in civilian applications, it might make sense where cost is usually a constraint. But in military, that is not the constraint. Military performance is always the first priority. Cost comes later. So I think it is a very interesting approach, and we need to see how it evolves.
We have time for one more question, and I think you're going to enjoy this one particularly. The interaction between weather radar and communications is also attracting a lot of attention. My understanding is that researchers in this community, like yourself, are especially concerned about sharing the spectrum with communications. Can you give us your perspective of the particular challenges and opportunities related to integrating weather radar with communications?
Yes, thank you for this question. And as you can see from my background, I have this 3-volume book coming out
Yeah.
on advances in weather radar, which I've been fortunate to co-edit this with Professor Bringy and Dr. Thurai from Colorado. So yes, weather radar. It's a community that and it's its own community. I won't qualify it as a smaller community nowadays. A lot of people are looking into radar meteorology more than before. There's something which needs to be investigated a lot. I would partition my answer into 3 broad areas on this spectrum sharing or spectrum issues in radar meteorology. First is by frequency. So which are the frequencies where weather radar operates? We need to understand that first, and what kind of interference they are dealing with. The second is the operation of weather radar itself. What are some new challenges that this kind of radar presents in spectrum sharing? And then finally, there are other systems which are allied with weather radar. They're not exactly weather radar, but they operate very closely with these systems, and how we can complement either weather radar or how we can investigate issues on spectrum sharing and those other instruments. So coming to the first, so weather radar nowadays, they operate across a wide band of frequencies. National Weather Service in the United States has about 126 contiguous, in the contiguous United States, 126 S-band weather radars. These are huge systems that National Weather Service employs. And we know there are communication services at S-band. And in Europe, most of the national services, they employ C-band weather radars. I think German Weather Service uses C-band, Meteo France as well, and so on. Even in UK, it's mostly C-band radars. And we know in sub-6 gigahertz, the interference with that C-band radar could be really something to be concerned about. In Finland, Finnish Meteorological Institute did a study a few years ago looking into what kind of interference spectrum sharing issues all these different kinds of weather radars may have. So S and C band we are very concerned about. And there are some news reports that there has been some interference from communication. Moving from there, we have X band. X-band radar, weather radars have become very popular because they are mobile. A lot of universities in the US and in Europe, they are using X-band radars because students can drive those radars in the vehicle, go near the storm and observe the storm using the radar. At X-band, we don't have a lot of communication services at this point. So there's the 8 to 12 gigahertz band. I think at that range, there isn't a significant of interference from communications yet. KU, K band, there are some weather radars operating in those bands, but I think there also, we don't have much concern at KU band, but K band, I think there are some concerns because that goes until about 36 gigahertz. And obviously, as you know, there may be some services, communication services in those frequencies. At millimeter wave, clearly, we have a lot of communications research going on at millimeter wave. Radars, weather radars have been operating at millimeter wave, but there isn't a huge concern at this point because most of the radars in those frequencies, they are vertical pointing. They don't scan like a mechanical scanning radar all around. They're just looking in one point. And that too just vertically pointing. There's no signal which is coming vertically down to that radar. So interference is not a huge concern for these kind of vertically pointing radar. There is some research from JPL on terahertz or low terahertz, as we call it, weather radars. But this is in a very nascent stage, I would say, with the advent of terahertz communications. And as you know, ITU has already allocated spectrum until 275 gigahertz, and active discussions are underway to allot spectrum beyond 275 gigahertz. So we will see what kind of allocation happens and if it affects any weather radar applications. But so far that band is also, I would say, is not a major concern right now. So that brings us back to these S and C band radars, where there is a very significant concern of interference. So that is by frequency. The second issue is what are some unique features in weather radar which we can exploit for, or we can learn from those features in spectrum sharing, while especially looking from signal processing point of view, what are some unique things we need to keep in mind? So the first issue is the nature of the target. Whether targets, they are not point targets, they're not simple extended targets, extended hard targets, it's a volumetric target. And the nature of this volumetric target is the source of all kinds of novel signal processing techniques in weather radar. So if we look into the spectrum of the target itself, the received signal spectrum, the target occupies a range of frequencies. Weather target has a Gaussian spectrum. It's fairly extended. It is not localized at just one or two frequencies like a point target would. It occupies most of the received signal spectrum. So if there is an interference, it would definitely, we cannot use techniques such as notch filters to remove the interference from the spectrum, because all of that spectrum has very useful meteorological information. So that is one unique thing about weather radar. Use of phased arrays is also fairly new in weather radar. We don't have the concept of MIMO radar yet in radar meteorology. People are looking into that, but as I mentioned, there are a lot of issues when you are dealing with volumetric targets. So I think currently we are at a phased array level in weather radar, and most of the solutions, if you're looking into any use of MIMO, that won't be applicable here in spectrum sharing. Finally, one attractive feature, as I had mentioned earlier, when we were discussing full duplex, was that simultaneous transmission and reception. Radar has been doing it for many, many years for multiple polarizations, and not just linear. In the initial history of weather radar, people have also used circular polarization. So all these developments in weather radar on the simultaneous transmission and reception, we could probably learn from it and apply it to the applications, the non-weather radar applications that we have discussed so far. So these are just some of the highlights of what is going on in weather radar, what are some of its unique features. And finally, there are other instruments that are related to weather radar or could be used to enhance the performance of weather radar. So in these, again, I would discuss three major points. First is, we don't have weather radars that are just used by national weather services in the US, Europe, or other countries. There are other radars which have the weather channel, and that might be affected from interference. For example, FAA radars, which we call as, which fall under this aviation meteorology. So we have FAA radar, like aircraft surveillance radar, ASR, which you see at most of the US airports, this big radar, on the terminals. The current ASR has a Doppler channel in the receiver chain. So while it is trying to detect these aircraft, it is also trying to access some weather information in that LE channel. terminal. So if there is interference in ASR, it will also affect the weather information. So ASR is one such radar. ARSR is also used by FAA in a different band. And then we have C-band TDWR, terminal weather radar, which is co-located with the airports, but not at the airport. And it was developed by MIT Lincoln Lab. And I think recently it has also been upgraded to two polarizations. So C-band has a lot of these spectrum issues. So TDWR would have these issues to look into. So we have these radars not used by National Weather Services, but other services. So FAA is one of them. Other lead instruments could be radar altimeters, which are mounted on the aircraft. So you might have seen this report from a few months ago when AT&T and Verizon had to stop their 5G services near the airports because they were interfering with the C-band radar altimeters. This is just a few months ago, and we are yet to find a good solution because those frequencies are interfering with each other.
But it seems they are more like a problem with the filters using the altimeters, because really the transmission shouldn't interfere. Like if you have a good design of the radar, right? I mean,
yeah. So
I'm a bit surprised with those news. It seems to me that is maybe an old design or bad design, or which did not account for possible transmissions. But I think it's shouldn't be a big deal. Seems.
Yes, so you are very right. It is an old design because radar altimeter was developed in 1920s, right? It's almost 100 years ago. This instrument was developed, and yeah, you can pretty much call it a clash of FAA and FCC. So FAA is more like, we developed this instrument first. Why are you asking us to change it now? It's almost an 100 years old instrument. Yes, but this did happen. Although if you look at specific frequencies, it's not like there is a total overlap of frequencies. There is a partial overlap because altimeters, they work at C-band, but only some of the frequencies were used by AT&T and Verizon in that. I think the lower part of that particular range.
Right? Yeah, to me, I think it's an issue with the old design. Yeah.
Yes, correct. So so we are looking into these other other instruments as well in the radar metrology. And finally, the other aspect that I want to mention is we have communication satellite links at Ku band and K band, millimeter wave, close to millimeter wave, we can say. And there has been a lot of research going on in multiple groups that could we use these communication satellite links because if the signal is propagating through the atmosphere from the satellite to the user terminals, it gets attenuated, it loses its strength as it propagates through the atmosphere. And that attenuation could be used to quantify rainfall rates. While weather radars are very expensive, and after 40 kilometers, S-band weather radars in the US, they start touching cloud tops. There is no information available for the lower troposphere for those S-band radars. Can we use these communication satellite terminals on the ground? And there are about 2 million of them worldwide, compared to weather radars you can just count maybe just a few hundreds of such units. And those weather radars are not covering all the regions as well, especially in developing countries. Can we use these communication satellite ground terminals and use this information about the attenuation? Because at millimeter wave, there is almost a linear relationship between specific attenuation, that is attenuation as a derivative of range, specific attenuation and the rainfall rate. Can we use that to supplement the weather radar observations? And there is a lot of nice research that is going on in this area. And an allied research related to this is, so this is more like, you can say, communications aided sensing, except that we are basically fusing the observations from the two, right? And another related application is where satellite signal is not used, but the commercial microwave links on the ground, they are used to harness rainfall rate information. There are works on along those lines also. So that is also an example of communication-aided sensing in weather radar. So yes, this is a full spectrum, nearly full spectrum or major issues that affect spectrum sharing in radar meteorology.
Okay, thank you so much. Thank you for all the information. It's a lot of information coming from a radar expert. Also an expert on your radar communication, but it's very nice to listen to all these radar considerations that not all the researchers are so familiar with. Thank you.
Thank you, Professor Nuria. It was a pleasure, and thanks a lot for giving me this opportunity.
Thank you.